didn't say recording. Share screen. I guess it's recording. It didn't say it though.
It has the little recording icon, that blinking red.
Here?
Yeah.
Oh, okay. All right. I wonder why it didn't say. Did I? Everything should be set up okay, I guess. All right. So let's see. Let me just get started here. So anyway, so this shouldn't be too hard. There isn't much to this, and there's not. All right. So there's two papers. They're both review papers, you know, so it isn't like really a subject, which is a disadvantage. But one is this thing in Nature Materials. So Nature's like a top journal, you know, hey. And they originally it was just one journal, and then they decided like they could make more money if they had like Nature Energy, Nature Materials, Nature whatever. So Nature itself, so they go by citation index, like macromolecules, like eight or something, I think. Nature Materials is like 40. Nature Materials is something like, I don't know, 20 or 30. So even though they spun off all these other journals, which is about 10 or 11 at least, each of them still has this huge, so there's plenty of room for journals, I guess, at the top, you know. But the problem is, like, you write a paper, usually it's going to be like, you tend to be wordy, so it'll be like 30 or 40 pages, you know. And this thing, they're only going to take 5 pages. But nowadays you can put like supplemental, so you can take your 40-page paper, take 5, and put 35 into the supplemental thing, which is kind of how these work. I'm not sure if this paper has supplemental because it's like a review, so it doesn't matter, but a lot of times. Anyway, these guys are from Manchester. One guy's from Manchester, someone else is from East China Normal University, which I don't know anything about Chinese universities, but Manchester is where they got the Nobel Prize partly for graphene, and it was shared with another school like somewhere else in England, you know. Manchester's is kind of like the, I don't know, the top kind of working class school. Like England has these Oxbridge, Cambridge and Oxford, and then supposedly they're the smartest people or something. And then Edinburgh is a good place too. It's almost like that, except it's spread out a little bit more. It's not the same. They got a lot of weird schools there. Like I was there on sabbatical. So, and then my daughter really likes Harry Potter still, even though she's old. So she came to visit, and we went to all the Harry Potter. In Oxford, if you go there, it's just straight Harry. In fact, Oxford gets like something like 100,000 tourists. It's like Disneyland a year. Okay, so it's like if you go to school there, it's like going to school in Disneyland, literally. They also have like Lewis Carroll, and then the poet Shelley and all those people. So there's a lot of like, so you get like the English literature tourists, and then you get the Lewis Carroll and the what are they, the trolls or something, Tolkien. So all that stuff is there. There's Tolkien Museum and everything, you know. So it's like basically Disneyland. And then the Harry Potter, like all the stuff, like the hall where they eat and all that stuff, you can see. But that's it all. Like if you go to Durham, that's where they fly around in the courtyard. If anyone likes Harry Potter, England's a great place to go to, because you can go to all the places where they filmed it, the original stuff, you know. And it's at all these universities and cathedrals and things. So anyway, Manchester's got a special place though. So they got a lot of Nobel laureates there. They had a really strong Polymer program, still do. So, but actually the Polymer program has gone off. This is in the center of England, you know. Like if you drew a picture of it, and right in the middle, it's kind of Sheffield, and then a little bit north of that is Manchester, and then Leeds. Wait, those are all the places where they're doing like polymer stuff, right in the middle. Like Manchester is a big place, and then Manchester's also got this nano thing, but some of the other schools kind of claim to it too. So nonetheless, like Manchester is kind of the best place. Is not like Oxford, Cambridge, or like we figured out that the London, whatever university isn't that old, right? So, but basically that's another good school. So anyway, I think it's a good place. Like it's a pretty good place. You know, I've never been to their campus, but I've been to Manchester. I haven't been to the school, but so anyway, they're there. So they have this history, and these people are at the Graphene Institute, I think, School of Chemistry, Molecular. Maybe not these people, but their Department of Chemistry. But there's a Graphene Institute there too. So, right. So they're looking at kind of making 2D structures, you know. But this is kind of a review. The idea is like, you know, you want to have a cloth and then you want to make it out of molecules. That's the idea. So part of that, so you can think of these as entanglements. So they draw the link between entanglements and this thing. So people have made this, like this second, these guys are at the, let's see, these are Manchester Department of National Graphene Institute, because they won the Nobel Prize for graphene. Right. I think they got it. Right. So they got original graphene. They just took graphite and someone took Scotch tape and like pulled it off. And that was how they won the Nobel Prize. It's just like, boom, there it is. And they figured out there was a lot of characterization, but they figured out they could get one layer. It wasn't an effective way to do it, to mass produce it, but they got it. Anyway, so it's kind of almost a joke, and then it becomes this big institute, you know, in a sense. So, but there's a lot of ways to get graphene now. Anyway, so these guys actually make something. So the point here is that they make a thing. This is the interesting part of this. They can blow that up. So they can make a sheet, a one molecule sheet of this weird shape thing. So it's like called chelating. So you take a metal atom and you chelate it into a ring structure. Like ferrocene is a diesel additive that cuts down on something. It's the iron's a catalyst to reduce NOx, I think. So ferrocene's one of these ring compounds that's really cheap. You can buy bottles of it. So, but that's kind of the most common kind of. So this is kind of like a crown molecule because it's got a ring that surrounds. This is like a crown of organics around a metal. Anyway, so you can take that and make it into a woven structure, then they can make that into a membrane. So actually make sheets and they can stick the membrane into a thing and do separations with it. I mean, they're not pumping it through it, but apparently it keeps the red away from the clear, although it isn't totally clear. So that there's different ways to do that. They end up with actual sheets of things. Other people don't, you know. So this is a nice paper. This is in Science. So these are all like, or this is Nature. It's all like Nature Science. So it's kind of like, I don't know. They're thinking that this is going to go somewhere. It's hard to tell if it really will, you know. So, and this is called, part of this is called orthogonal chemistry. So you do like a 2D chemistry in plane. Then these rings due to stereochemistry are like at right angles, right? And then the rings have like pi-pi bonding because they're conjugated, so they can link up and form kind of layers. So that's called orthogonal chemistry is one of the terms they use. So they have a bunch of catchphrases. And then everyone's going to talk about woven fabric. And then the idea is you're going to have controlled pores is one thing. And they say it's going to have super strength because it's going to be, the strength of the covalent bond is really strong, like much stronger than metallic bonds. So it's theoretically, I mean, you can make bulletproof vests out of polyethylene, put it that way, if you can orient the chains straight, which they do, you know. So there are bulletproof vest polyethylenes. So right, covalent bond is strong, stronger than any other bond. So basically it can be the basis for really strong 2D sheet things. And then the guy in this paper talks about making hats out of it. So molecular hats, and then you can put that on your molecular machine and you could have a little guy running around. Make a molecular snowman if you wanted. So anyway, that's the theme of this. That's why it's appealing to people. But so anyway, the point of this with us is that he goes through the whole history of entanglements. So these are also MOFs, MOF, metal organic frameworks. You see these things, like there'll be a meeting on MOFs. And like everyone's doing this. So this is an anion, so it's like chlorine or sulfate. Then these are some kind of metal atoms. So the metal and the anion have a relationship. And the organic is there. So you can make a crystal. You can make like a perovskite crystal out of metals and cation and anions. Then that crystal can have certain arrangement, and then you can get rid of the metal and cation and just have the organic framework that's left from that. So people do MOFs, MOFs, to do things like catalysis. I mean, you can isolate the metal atoms that way, and then they can be highly catalytic. You can build a porous structure that's better than zeolites, or better than, so basically as a framework for catalysts. So petrochemical industry is interested in MOFs. I'm not sure how much MOFs have actually had an impact, compared to like metathesis synthesis and things like, which remade the entire polyolefin business. But so MOFs is still unproven, I think, in some sense, although a lot of people are working with MOFs, and then some people are working with this woven thing. This is more like the woven fabric thing is just kind of beginning, means it could fail or it could actually go somewhere. And the MOFs are pretty well established. Like there's people kind of my age that are doing MOFs that have been doing that for the whole career. So MOFs has been around. Anyway, so the point of this is that he goes through and says like, tube model's great. Like there it is, the tube model, and that's good for like this kind of disordered thing. But if you want to have concatenated rings, which is like Olympic rings, then you're going to have some other model. And those models existed before the tube model. A guy named Tobolsky, who was at Princeton, came up with kind of a lot of models, in the 1940s and 50s. And one of them was this kind of slip link model, which was picked up on again after the reptation in the tube model. And then the slip link model was rejuvenated because to alleviate the problems with that they couldn't get power 3.4 out of this. Molecular weight versus viscosity versus molecular weight goes to 3.4, not 3. This predicts 3. The slip link model can kind of alleviate that. And then there's this called the slip spring model, right? So then you can think there could be a lot of other models. But nonetheless, the most robust one and accepted one is this tube model, right? So that's kind of the standard bearer that you need to know about. Anybody's going to do anything, they're going to use that model. But then when people start looking at what are the problems with that, they get to these other things. So there's 99.9% is this thing, and then there's these other groups kind of messing around with stuff that use these other models, right? So he mentions those and he gives some good references to them. So, and then those models are more appropriate if you're talking about this kind of weaving of molecules, because there's no tube in this. But it's good, definitely has slip links. It probably has like spring things. So he goes through and shows like kind of how that could work in a general sense. Like there's no science here, it's just like a cartoon thing, which is typical of a Nature review, right? It's basically it's like one level up from popular science in that it's dealing with something that's actually could go somewhere, but not much above it. So in that he's given good references too, so anyway, so that's here. It's kind of to look at, and then there's some questions about figure 3, the 4 models, explain the difference between the models. So then I gave you all the papers. So I'm not sure how much you can get out of these. these are just these are just ways to make woven structures. There's different methods to do that. These are guys at Berkeley. So JAX is like a tier under Science and Nature, but not much further. Journal of the American Chemical Society. These are also 5-page papers, you know, so like I think Nature's 50, Science is probably 45, citation index. JAX is probably 30, like Nature Materials, kind of like on that level. So it's a little bit lower than the others, but the ACS journals are kind of higher ranked because there's a lot of them and they're all pretty good. So this is kind of typical orthogonal chemistry. It was linking across and then it goes normal to that. So I don't know much about orthogonal chemistry, but that's the limit of what I know. So anyway, this is another short paper on how those this is kind of the British version of American Chemical Society. Just talking about different ring structures and things. It's just of interest, like paper related to that. These are all pretty recent. Like this is 2018. I think that's the oldest one. And then this is the papers on a different models. So this is the slip link model. So Doi worked with Edwards on the tube model. So Doi's a famous guy, and he wrote there's a short book that's linked on polymer physics. It was written by Doi. So anyway, this is his version of the this is the reference for the slip link model. He says, I mean, if you read it, it's kind of interesting to read the beginning. He talks about Tobolsky, see Green and Tobolsky, the Princeton guys from 46. And then he says, like, I'm rejuvenating that because there's a problem with the tube model. And then he goes through it, you know. He shows that there's some advantages to it. So basically, I'm just asking you to kind of glance at it and try to get something out of it, whatever you can get. This is also a review of the slip link model, and it's got this business of the neutron. So this is that thing I was talking about. The spin echo is the thing where you polarize a neutron and it goes through the sample and it depolarizes it. And then you measure the polarization of it after, and from the change in the angle of polarization, because it's got to do with the time that it's spent in the sample, you can tell the relaxation time of the material from that. So he's saying that the spin echo data doesn't match the, this is from Leeds. So the Leeds had the polymer, were the polymer guys for a while. Then they kind of split up and went to different schools in England. So, but Lichtman was a guy at Leeds. This is from 2005, so he may have moved on by now, you know. These are kind of typical. So you see a decay and the intensity is a function of time, and it's a correlated intensity. So basically, this kind of pattern is similar to, let's see, dig that up. I want the PowerPoint. I have to hide this to get it. Where's PowerPoint here? Again, this. Into this somewhere. This thing. So basically, there's going to be a decay in the signal. If it's Rouse dynamics, it decays to 0. If it's constrained by the tube, it ends up at a value, and where that cuts off in kind of Q, U is a number that's time and Q. So it cuts off at some size scale. That's how you measure the tube diameter for the tube model. So basically, you have S of Q and T. So it's got the Debye function for the chains. And then it's got a time dependence to it too. That's kind of this exponential minus T over tau kind of thing, which gives you a relaxation time. If it's a Rouse chain, it's just free. So it relaxes at infinite time. It totally relaxes. And then, so it's kind of like the Rouse relaxation time somewhere in the middle here. And then it cuts off earlier if it's confined within a tube, because once it reaches the size of the the tube diameter unit, it will relax there. It can't do any more motion. Right. So you have a size scale that changes with Q. Q is here. So as the time that tau changes with Q, large Q is small size. And then if you go to low Q, which is up here. So basically you get the tube diameter from that plot, which is the same as the plot he's showing here. And this, he's saying that the Debye function that you use isn't going to be right in the time range where you have to look at a Q value where the Debye function, he argues, this paper is about arguing about the function, but basically he says that the tube model won't work, but the slip link model will work to describe the actual data. It's a pretty complicated paper. So I'm not sure what you get out of this, but you can glance at it. Then this is the other model that the guy likes because it's exactly the thing he wants. So this is the idea of this topological model for entanglements. In other words, the chains are nested together and they're topologically locked. So they have kind of a physical crosslink. And that's what gives rise to this paper 51 talks about that topology thing, right? And how that could be used as a model to talk about like transport and polymers. They do some simulations that kind of verify the idea that the topological thing is the important thing. So he likes that, he cites that paper. This is the same thing, except it's older, 67s by Edwards. Oh, Edwards, I guess, was at Manchester, huh? But he ended up at Cambridge. So I guess Cambridge pays more. And you get to see all the Harry Potter stuff. So. But I'm not sure there's any Harry Potter in Cambridge, actually. I haven't been to Cambridge. So. And Lichtman is at Leeds. That's the same paper. Right. So I don't know it's there. Anyway, so that's kind of that paper. So it says, look at those papers and tell me what the slip link model is and what the topological model is. And the references are there. What are the problems with the tube model that those alternatives address? So there's those papers. I mean, the main one is this viscosity. The slope's 3.4, not 3. But there's others like diffusion coefficient. There's problems with extensional flow with the tube model. So, and I guess next week I probably talk about extensional flow and some other things like that. But basically, the tube model can't explain why, like we had the pain effect with rubbers. So if you stretch it, then the modulus drops. So if you do a dynamic measurement at higher strain amplitude, the modulus drops. Like the tube model can't explain that. Okay, so these other models can explain it. So there's high strain, there's the viscosity thing. The diffusion coefficient number isn't perfect. None of the numbers are perfect. The tau, the diffusion coefficient, viscosity, and modulus, none of those numbers are perfect. They're all off by a slight amount. I mean, if you call 3 a power of 3.4 versus a power of 3, slight. Because actually a power is a big difference, but in the actual parameter you're interested in. So they list a bunch in there. Just glance and see what you can get. I'm not interested in the comprehensive. Just kind of look at it. And then what else is in here? This is looking at those woven fabric, shows a filtration. That's that one that actually shows a device. Explain what's meant by orthogonal chemistry. So you can Google that. You can read what he says about it and how it relates to the concept. And so he's setting up orthogonal chemistry so you can set up molecules that are woven together. So it's possible to do that. And which model would be appropriate? So it's going to be like either the slip link model or the topology model would be appropriate to this kind of, because you're weaving it. So it's not a random entanglement, right? So then there's this issue like, is this bullshit or not? So I mean, they're going through a lot of chemistry. It's pretty fancy chemistry. They can actually end up, one of the groups can actually end up with a membrane, for separation. So that's kind of interesting. But there's already exist like beta sheets and proteins. So there already are fabrics in your body, like your body makes beta sheets. If you take an egg and whip it up, you rip apart all the native conformations. If you do like X-ray scattering on that, you find out that the proteins have made a bunch of sheets. It's all sheet structures. So just taking an egg in your kitchen and whipping it to death and making like whatever you make out of that meringue. Yeah, that's this sheet structure. You already made it in your kitchen. You're eating it. It's like, how is that different than the sheet thing that these guys are making? And it also comes in nature, like amyloid fibers that cause like cataracts. And they used to think caused dementia and stuff, But basically, I think they've proven that it doesn't cause dementia, but it still causes cataracts. Like the UV light goes into your eye, the proteins in your eye get denatured. When they denature, they naturally just form these sheets because they hydrogen bond across. And those sheets stack up and then they make white things in your eyeball, in your lens or whatever, right? Then you can pull the lens out, put a new one in, plastic one. So anyway, so beta sheets are all around. They're easy to make, You don't have to do anything. You just take any protein and beat the heck out of it or heat it up or do anything to it that's going to break it apart and it makes sheet structure. So that's a fabric, if you want to look at it that way. And then polymer crystals, if you make a single polymer crystal, that's already a woven fabric. Like any cartoon of it shows, the first thing you think is like it's a woven fabric, especially if you have a tight knit, like tight turns at the surface, right? So like, how is a single polymer crystal different from the things that they spent a lot of money trying to make if it already exists? And then also, like, if you look at asphaltene, pi bonding, it makes sheets. So that's a fabric. It's like, how is it different? Like, why? So the thing is, like, what do you think about that? It's kind of like a goofy question. But basically, you wonder, like, if no one knew about asphalt, and then you discovered it, could you pitch it to nature as a fabric and then make something from it? Who knows? And then the last question has nothing to do with that. It's just like I was looking around for papers and I ran across, it's another review paper though, which isn't good. But it's a review paper. So it's this Langevine who's no relation to the Langevine. And I looked it up because I thought, okay, it's got to be a relationship. It turns out there is a huge relationship from the original Langevine. There's a whole tree you can get on Wikipedia of all the people. This isn't one of them. This is, in fact, a woman who married a guy named Langevine who like sells cars in France or something. So not related, as far as I can tell. But she did change her name. So unlike the Jones guy who hyphenated. So anyway, so this is just the nice thing about, I was talking about like bubbles and drops and this, like, nice thing about this paper, it covers like everything we've covered. Like it's a review. It's like a greatest hits of all the polymer rheology. Like they have the equation that looks confusing, that's really simple that we talked about. And they show the crossover, plateau modulus. They talk about what happens out here. So they talk about this nice paper in the sense that it summarizes everything. They show shear thinning, shear thickening, Bingham fluid, where you have a lag here, like catch up, you have to whack it to make it flow. And then they show this equation, which I've never seen before. And it turns out this is like an important equation. So it's called the Krieger formula. And Krieger was a guy at Case in Cleveland, right? And this Doherty, okay, this is like his dissertation, I guess. So he's at Firestone in 1949 or something, 59. But all right, there's something really weird about this. All right, so you take Doherty, and you say like, the derivation. So they derive a nice equation for rheology, which you can read, and it's but it's had nothing to do with the question, because this derivation of the Krieger equation isn't the equation he ends up by, the thing he does. So he says like if beads are under a shear field, then the difference in velocity from the top to the bottom is gamma times the distance. So gamma by 2 gives you the velocity that turns the thing around. And if two things come together, you get this problem. They're spinning and they're spinning in opposite directions, so they have to couple together. Like that's causing a lot of twice the loss of energy right there. So they want to get rid of that. So instead of turning like that, they'll couple together and turn as a unit, like a dumbbell. But something in between would be like that. So they develop an entire thing about a kinetic model, like Smolakowski equation for particle aggregation, except based on this kinetic model of rotation. So Smolakowski, people that do aggregation of particles just do kinetics, they bind, they unbind. So there's a reaction constant for each thing that happens. And you do a differential equation for the entire thing of building clusters and things. Kind of a famous thing, but basically they model it after, especially in 59, it was a popular item. So, and if you do computer simulations of aggregation, it's important. But so anyway, they do the same thing like a kinetic model. So these are all kinetic constants to get the populations of the dimers and the monomers. And then you can figure out from that basically the viscosity of the system somehow, right? So you get it's related to these kinetic constants. So that's a nice theory. I mean, I think that's worth a PhD, like they went through that in 59. So they end up with this equation, which isn't this Krieger equation. Like that's what's shocking. Like you go through all that, yeah, that's great. I love that theory. So I said, like, where did this equation come from? And then it's not the same equation, yeah. It's like, so you go through that. Then they go like, okay, so this guy Mooney, okay, who wasn't part of the Moonies or anything, he's just happened to have the same name. I'm not sure what nationality that name is, but anyway, so Mooney came up with an equation that works pretty good. Let's see.
Is that the Mooney viscosity guy?
Yeah, it's the Mooney viscosity. It's a Mooney. There's also a Mooney-Rivlin equation for polymer mechanics. So Mooney was a guy at Firestone in Akron, okay, and he got his degree at Chicago, his PhD, and then so anyway, let's see, where was I? So this is the equation you want. You have this paper with a nice derivation in it for some other equation. Then he says like, then he just says like, oh, this guy Mooney came up with this Mooney's functional analysis, AKA bullshit, came up with this equation, right? And he says that equation, all right, so he says his equation works pretty good. Like he's modeling two different systems here. This is his equation, the one he derived, Méron's data and Levy-Pascal's data. And they can fit the viscosity versus this parameter he had, the volume fraction. Lambda's the absorption of the water or something. It has soap on particles, and then P's the packing factor, like how. So he says it's 64%. If you fully pack spheres into face on a cubic, you get 74% space fill. And if you randomly pack them, you get something like 50. And he says like 64 is somewhere in between those two. That's if you have spheres, that's as much as they could fill space. So you have to like normalize the volume fraction by that packing factor P to get the right number out of this thing. That was Mooney's conjecture, and he raises it to this power, but he doesn't say why. The power is the same packing factor times the intrinsic viscosity. So this is like insanity. It's total insanity. There's no reason to do this, right? See, so he says, that's well and good, but if I just, oh no, so he says this is a modification of Mooney's functional analysis, right? And he says the derivation of this will be published elsewhere. This is the equation. This is actually the equation, right? Because he's got the fraction times the intrinsic. So we have 2.5 is the intrinsic for spheres for the Einstein equation times the fraction. This is the packing factor, the 64%. C5 is 64%. Then the volume fraction over that thing. So that's the Krieger thing, right? And then that's that's this equation, P, and V is, or nu is a volume fraction, right? So that's he just says, so you go like, okay, then this has got to be in this guy's dissertation, right? Because this says, so that's it. That's the derivation they give, you know. So basically, you go back and you say, well, Doherty, whatever, Firestone, this work was part of the doctoral, so he's got to have it. Like the dissertation is where you put all the dirt, like everything that you did. So you go look for Doherty's dissertation, you know. Here, so I'm just going to do that. So this is where it gets weird. Wait, where did Doherty go? Exactly the same name, okay, but a different person. And this is 1959, right? So you think like, it's got to be a dissertation from 1959 in Ohio, right? Thomas Doherty, dissertation, whatever. And you find out kinetics, this is his dissertation, look, from Ohio State University. But it's got nothing to do, it's like a different Thomas Doherty. It's about homologous series of substituted lactones. Who this Thomas Doherty later became famous, like he invented chemotherapy with lasers. Like when you put a chemotherapy agent in and activate it with lasers, he's the guy that invented that. So he went in 1970, he quit his job at some petrochemical company and then went to work for like somewhere NIH or something, and just said he wanted to cure cancer, and he did cure it, like with this laser thing, you know. So he became famous. So it's like an institute at Ohio State, like named after him. That's why I guess is anyway. So, but it's all right. So where does that have to do with this stupid guy? All right, and that was 1959. This is in 1959, exactly the same year, exactly the same name in Ohio. You know, odds for that are probably pretty low, unless something is weird about this that I can't figure out. But
maybe it's just common names.
I mean, come on, that's an Irish name, right? I think. I mean, that's a pretty Irish name, Thomas Doherty. So I don't know. There's not that many Irish people in Ohio, I don't think, are there? I mean, there's some, but it's not that popular. Who knows? It's really weird though that Thomas J. and in Ohio, you know, and both get a PhD in 1959 when it wasn't that popular to get a PhD, you know, so pretty weird, but it happens, I guess. The odds for that are pretty low, you know. So anyway, in 2013, I think this is 2013, these guys from Darmstadt, Germany, derived it. And to derive it, so they got the Mooney expression. So if you take log of it, NR is the viscosity over the the solvent viscosity, so it'd be log of that is this thing. So that ends up being the Mooney equation somehow. So they derive it here in section D of this thing.
They say something like, yeah, we couldn't find the original derivation, so we had to do it ourselves.
I mean, it's like 1959 to 2013, you know. Section D, that's F. This is 2 sections before that. Anyway, meantime, so here's that equation. They just substitute this 41 into 15 and they get that. They get it. And they do it by a weird way. They don't look at, like the Einstein equation just adds the volume fraction n times the intrinsic. They do as differential steps, like it differentially adds small pieces of the stuff in. I mean, it might be kind of, so they added in. So this was based on a thing these guys did in 2009, the Su and Wei in Taiwan, which is probably an overlooked paper, you know, but basically they almost derive the Krieger equation. They get to this point, but it's a little bit different somehow. And it looks exactly the same. Anyway, Su and Wei derive it, and then these Germans from Darmstadt derive it too. So the derivation is there. It's kind of a weird derivation. It's a little bit different, but I thought you could look through it and see what might reinforce. And then, so so anyway, because he mentioned Mooney, you know, so Mooney's kind of important. We haven't mentioned him, I guess. So Mooney's got an equation for viscosity too, which is this equation, which kind of looks like I mean, the original Krieger says that he models it on the Mooney equation. This is the Mooney equation for viscosity for suspensions. And Mooney derived it for latex, for rubber latex, like when you have particles of latex in water, kind of. And then Krieger later made a better equation that has that other functions. That's kind of, I guess, widely used in when you get to particles that are more dense and like dilute. Even though the Krieger derivation is for dilute conditions, as is the Mooney, I think. So these are equations that are used for high concentration. One of these things shows the situation. Like the review article, one of these shows how the viscosity shoots through the roof, how these equations are necessary. I forget where it is, but anyway, basically the viscosity goes along and then shoots up, so that these equations take care of that at high concentration. Anyway, so as long as you're talking about Mooney, so there's two things that Mooney did. One is this idea of modulus, right? So anyway, this isn't in the quiz, but since we're on Mooney, I'm going to do this. This guy doesn't want to do that. Oh, it's not doing anything. If I broke it or something. Oops, I hit it too many times. There, it's back to normal. All right, so all right, the Doherty thing is really weird. There has to be an explanation for that. Maybe there were like, I don't know, how two people get the same PhD, exactly the same name, same year, in two different schools in Ohio. The odds are low. So if you have a crystal, right, and then you pull it, so you get the force, and then the atoms like separate somewhat, right? So the actual atomic spacing changes. That A like becomes larger, right? And that's how you get this idea that you have force and then times the modulus, the Young's modulus. It's called Hookean elastic. So that's called elastic behavior. Right, so basically the density drops. The density of that material drops when you do that. So when you pull on a piece of steel, you actually lower its density. And that's the reason that it springs back. Right? But if you take rubber, so that's called dilatational stress, like the density has changed. Right? So if you have a material, the alternative, so that's for a compressible material. So you can compress it and reduce the volume of it, increase the density. So liquids are incompressible by definition, and a rubber and a lot of plastics are incompressible. The first assumption is that a plastic or rubber is incompressible, which means that it can't follow Hooke's law. You can't have the stress is a modulus times a strain unless you're in shear. So in shear, you can get that because there's no dilatational stress in shear. So if you do tensile measurement, if you pull on it, then you get dilatational stress. If you shear it, there's no dilatational stress. You're just moving the deck of cards. So we aren't ripping the cards apart, they're just sliding along shear planes. Right? So for shear, you don't have to worry about this, but in tensile, you have to worry about it. So that means that so Mooney figured out how to deal with that. Basically, how to deal with incompressible fluids, or like tensile for something that's incompressible. And you can't, so if you plot stress versus strain, in Mooney's equation is in terms of elongation. So strain would start at 1, elongation starts at 0. So lambda is the number he uses, which is elongation. It's like strain minus 1. So okay, for the metal, that thing goes just like linear, and you have the modulus, and then it breaks. Or for glass too, like polystyrene glass or something. You actually change the position of the atoms. For rubber, that thing looks like this. Like it never has there's no linear part to it. There's a bunch of linear parts, but there's not one that would work, So there isn't a modulus to it, not like that kind of modulus. So Mooney Rivlin, I'm not sure the relationship, but they figured out how to do with that. And then if you stick a rubber band into an instron, you can see that happen. This guy's like slow. Okay, we're here. So this is a paper from Bangkok, Thailand, from 1998 in the Journal of the Science Society of Thailand. But the nice thing about it is they just simply give you the Mooney-Rivlin equation, which is what you do stress and that elongation ratio. Then the two Mooney-Rivlin parameters, C1, C2, and they tell what they are. C1 is the crosslink density. So that's like your modulus from the rubber elasticity idea. And then C2 is something else. See what C2 is. Slope because of C2, value of C1 uses a statistical crosslink density. So that's like your rubber elasticity thing, the molecular weight between crosslinks. So 1 over molecular weight between crosslinks gives you this crosslink density. So C1's the thing you want to get. And then C2 has to do with the chi parameter. C2, I mean, he simply just does it here. That's the nice thing about this paper. So you don't have to read through all kinds of crazy stuff. So you take a rubber band and you stretch it, and then you plot the stress divided by this weird function of the strain, and you get a linear plot. Whereas if it's a modulus plot, it's not linear. So you can't get a modulus. So here you can get the rubber modulus from this plot. That's called a Mooney-Rivlin plot. So that's the other thing about Mooney. Like this is an important thing because basically a lot of times you're doing tensile stress on something like skin, or jello or anything, basically you can't get a modulus. You can't do a stress strain plot. This is like one of the most popular mistakes people make in polymers, is they stick it into an instron of some kind, stretch it, and they expect to get a modulus from the slope. You can't do it because it's not a linear dependence because it's incompressible. You can do a shear measurement. That's why shear is better. So shear is just going to be linear, but a tensile doesn't work. So if you want to read the nitty gritty of that, some of it is in this guy, Roland, who's a guy. Roland's a famous guy for glass transition and things like that. Naval Research Lab, which is kind of a weird place. Like there's a place in Washington, D.C. is Anacostia, across the Anacostia River from D.C. It's a place where during the Civil War, after the war, all the troops went to Washington and they wanted to get paid. They wanted money, for fighting the Civil War, which they weren't giving them any money. So they camped out in Anacostia. It became like, also during the Depression, Anacostia became filled up with Hooverville stuff. So it's kind of like the wasteland of DC in a sense, Then now it's like a serious ghetto. Like you can't, if you drive your car through there, get a flat tire, just keep driving, So Naval Research Lab is there. It's also where the sewage treatment plant for DC is, So it smells. Kind of a funny place, but they got a lot of money for research, but basically, and Roland's a famous guy in the glass transition, but nonetheless, Anacostia is a pretty weird place, DC. So he goes through like the theory of it. So you can see it's going to be tensor math and things. So it's not particularly nice, but basically he ends up with the Mooney-Rivlin plot and shows that it's kind of linear. So the high strain is over here and the low strain is over. Low strain is at the high end and high strain is at the low end. So it deviates when the rubber crystallizes. If it doesn't crystallize, this would be linear all the way through. So anyway, this is just the stress strain plot. You can see there's no modulus part to it. But you can take that same data and get a linear plot with a linear equivalent, so that works, So the incompressible idea works. So is that, and there's some other like slides. This guy Hervé Morand at Virginia Polytech, he's retired now, but he's got some slides on this. I mean, basically, if you want to see some simplified versus the other one, it's in here. But anyway, I just thought I'd throw that in because we didn't talk about it. It's pretty important. When we do the characterization lab, we used to do a lab on that. Like here. This data and stuff, if you wanted to play around with it, but I know one will. Where that is here. So I haven't taught this in a few years, but the second experiment is like tensile measurements. The data is here for basically a rubber band. You can swell it to change the cross-link density. So basically this thing you can play around with. These links, a lot of the links are from there. So anyway, I guess that's about it. The quiz, yeah, so the quiz isn't really, it's not about that, but basically it just says like, try to derive that equation. Try to go through that derivation. It's like a differential. You have to do an integral of a differential equation to get the, it's kind of funny, the guy didn't publish and you can't get the derivation. And even though they cite that paper, it shows you how these citations, you run into that a lot. Like there'll be,
They just find a formula, but that formula was just like
the
yeah,
lane
I just
turbine.
came up with this formula and it works.
Yeah, I mean,
It's
like
okay,
the,
let's do this formula.
what's it called? That scattering function, with the 1/1 plus the square thing. That's a footnote in a paper about another subject. Yet it's that paper cited like thousands of times for that equation. So it's the same with this Krieger. That Krieger paper has been cited like I think 500 or 600 times, something like that, and it doesn't have the derivation in it. So it's just kind of isn't there. So it's kind of an interesting story, hopefully. So we got 2 weeks left. I still haven't decided what to do. Like usually, somehow I went through stuff fast this time. I think I skipped something, but I can't figure out what it is. But basically, I'm thinking about a couple different options. One is this extensional viscosity and stuff. One is like do computers simulation and do machine learning and artificial intelligence and the Internet of Things. And there's a couple other things that I could do. I mean, those are both like 2 lecture things, maybe could fill up a week. There's something else. Oh, like block copolymers, nanocomposites. So it's a bunch of different things that are kind of a little bit topical, but a little bit becoming more mainstream, I guess. Oh, and then the circular economy could do that too. Those are kind of topics. Like every meeting is having whole sessions about that, physics and chemistry. So probably worth you just say what people are contributing to that if you want.
Circular economy with polymers.
Yeah, like what are people doing? I mean, there's a lot of things going on. A lot of it's chemistry, but there's some physics. Well, we've seen some like this idea of having these cross links that you can break, right? So the idea of that partly is circular economy. So you can do that with, so rubbers are a big problem, like tires, you can't recycle, You can burn them, you can turn them into playground stuff, as long as there's no steel reinforcement in it, And how do you even sort that? I don't know, but so.
Supposedly there's some sort of devulcanization process, which I know isn't a real thing, but they call it devulcanization.
Yeah, no,
Yeah.
guys up at Akron are doing that. I mean, there's a guy in the polymers engineering part of Akron that's got a whole, basically it's a pressure cooker,
Yeah.
and you make goo out of it. And the goo you can make into diesel or something if you want,
We
I
put
think.
devulcanized rubber, ground devulcanized rubber into
Asphalt,
asphalt.
really? Yeah, that makes
Use
sense.
it as a modifier.
Yeah, with high pressure, but it costs a lot, I think, to do that process.
It does.
They put the-
Is that stuff cheap?
No, but
Yeah, you
ground-
stick it, most of this is like start off, you stick a platinum catalyst into it. Platinum catalyst isn't reusable because you stick it into goo. So basically, you turn it, taking rubber. I don't know. I was just reading somewhere, there's 7 gallons of gasoline in every tire. Whatever that means.
Or the carbon content or the energy to get out of it, like.
Well, the total amount of gas, total amount of oil that it takes to make a tire is 7 gallons.
Gotcha.
So if it's like $5 a gallon, it's $35. So it's just the material, I guess. Just the crude material.
So for the 6321 crack spread, which is where you would get that distribution, 6 barrels of crude oil makes 3 barrels of diesel fuel, 2 barrels of gasoline, and 1 barrel of petrochemicals and heavy products.
Interesting. Anyway, they were saying the tire is going to go up in price because oil's doubled. So basically the $35 goes to 70.
So you're saying buy my tires now.
Apparently, I'm in that position of buying tires. Yes, that's exactly what I was thinking.
It's like, I could wait another.
It's like the car
6
thing. I
months.
waited to buy a car. I could have bought it last summer, and then like now it's hopeless. It's totally
You're just
hopeless.
like, I guess I'm just gonna stick with my car I have now.
Yeah, well, we needed, like my daughter took my car to California and wrecked it, like last in December, November or something, right? Totaled. So you have 15 grand from that, from the insurance, but basically to replace that car is like 25 or 30 now, if you can find it, you know?
I've heard stories where people have like they buy a Tesla for like $50,000.
Yeah,
It gets totaled, but the cost of a equivalent replacement
yeah,
is like $70,000. So
Yeah.
they got like $72,000 from their insurance, even though they paid $50,000 for their new Tesla.
oh, that's a good deal, yeah, because you get a tax rebate, you get the full price from insurance. Insurance won't give you'll never make out from insurance, so
Not
they have
used
ways to figure it out. I mean, they have ways to gyp you, I mean, it isn't gonna work.
we
you know.
had to really fight with the whatever they claimed equivalent car was. It's like, no,
It's
our car has,
hopeless.
we had like you're showing us equivalent cars with